They are going to be given by Rodica Borcia and Untitled Borcia. The first one is called phase field models for two fluid systems. Both are coming from Brandenburg University of Technology.
Thank you very much. So I am Rodica Borcia from Brandenburg University of Technology, Cottbus in Germany. I work in the group of Professor Michael Besterhorn, Department of Statistical Physics and Nonlinear Dynamics. And I'll present phase field models for two fluid systems, numerical simulations done for different geometries in the last 10 years. So, a short overview. First of all, I'll present the phase field formalism. How can apply this formalism for describing the Marangoni convection in a two-layer system? How can be extended the problem for describing drops and bubbles, contact angles, pattern surfaces, coalescing of drops consisting of different but perfectly miscible liquids, and at the end, conclusions and lines for the future work. So this was our first statement of the problem. A two-layer system, a liquid-vapor system heated from below, the temperature top and bottom assumed to be constant. If in the classical model, we have to write 2 times the classical system of equations for the liquid and for the phase, and to impose a lot of boundary conditions, we choose another way. We choose to use a continuous model, the phase field model, which will treat the problem continuously from liquid to gas to vapor, and in this way, the interface conditions will be eliminated. So, in this phase field formalism, we have to introduce an order parameter, which can be a number. In our case, we used a number with physical meaning, the scale density, assumed to be 1 for the liquid phase and 0 for the vapor phase. So we have here the liquid, we have here the liquid, here we have the vapor, and here we have a diffuse interface. In this case, supplementary terms have to appear in the classical Navier-Stokes equation, and this can be derived starting from the free energy functional of the system and using the Lagrangian formalism. So we choose the free energy density having two terms. The first one describes the free energy density for an homogeneous system far away from interfaces. So assumed to be a double well potential, a symmetrical one with 2 local minima, one corresponding for rho 0, that means for the vapor state, and one for rho 1, that means for the liquid state. The second term in the free energy functional describes the contribution of the interfacial energy. This K is a parameter which can be controlled in our simulations, and this term integrating through interface will give the information about the surface tension coefficient. So we minimize the free energy density for the equilibrium state using the Lagrangian formalism, and we obtain here a stress tensor which includes also the contribution of interface of the capillary forces. So we have in the Navier-Stokes equation a supplementary term. We can observe that this term disappears when the system, when the fluid is homogeneous, so that means in the liquid and in the vapor phase will not have gradients of the density, and this term acts only at the interface between the liquid and the vapor and will assure the balance between the capillary forces and the viscous forces, exactly like in the classical models. Okay. So how to describe the Marangoni convection in phase field model? We consider that the energy coefficient decreased with the temperature because the surface tension coefficient decreased usually with the increase of the temperature. So we have a temperature placed in a gradient of temperature. Here it's hot, up it's cold. In the system appears some perturbation of the temperature, some cold and hot spots along the interface. This will produce gradients of surface tension and pushing forces from lower surface tension to higher surface tension. And if the temperature difference top-bottom is enough high, so surpasses a critical value, will appear convective rolls in the liquid and in the gas phase, in the vapor phase. Okay, so we assume in our model that the K depends on the temperature. We need an equation for the temperature. We'll take a second equation, the heat equation, the energy conservation. And we started here with our simplest model for the incompressible fluids. The parameters eta, the dynamic viscosity, the thermal conductivity, and the specific heat are assumed linear function on the density. And we are in the case of incompressible fluids, so we work with the condition divergence V equals 0. In place of the velocity, we have worked with the stream function. And the profile for the density remains constant in the time. So we have the interface at the middle. It was the scale between 0 and 2. And this parameter describes the thickness of the interface. So we started with a linear stability analysis, assuming small perturbation for the velocity, in fact for the stream function and for the temperature. We have scaled the equation and reobtained very similar parameters like in the classical model. So we have the Marangoni number as control parameter connected with the temperature difference top-bottom. And we have represented here from the linear stability analysis the critical Marangoni number and the critical wave number versus 1 over L. And we can see that in the limit of sharp interfaces, so when the interfaces become sharper and sharper, we obtain a saturation which corresponds very good to the limit given by the classical model. So this is for the occurrence at the interface, at the instability, the Marangoni instability. It's an instability with threshold. We can see how it looks, the growth rate, the real part of the growth rate with K. Okay, in this case, appears only as monotonic instability, so will not have the imaginary part. And now going on for describing the fully nonlinear evolutions, we have represented the temperature and the stream functions at different moments of time, starting from an aleatory distribution. So we can recognize the pattern specific for short wavelength, wave instability, for the Marangoni instability. We can see that the interface occurs in a natural way near z equal 1. And we have here a discontinuity in the temperature pattern because the thermal conductivities are different in the liquid and in the vapor phase. And here the red colors means maximum of perturbation, blue color the minimum of perturbations, and here we'll have negative stream function, positive stream function, so we recognize the convective rolls in the liquid and in the vapor phase. Now the next step is to consider the compressible fluids. So we need an evolution equation for the density. We'll take the conservation equation, and going on now to present a picture from nonlinear evolutions. We represented here the velocity fields in the liquid. Here is the liquid and here is the vapor phase. And we can also observe the interface deflections. So here is the interface and there appears small variation of the density, pushing from both sides. Okay, so now the next step was to develop this model for droplets. And this problem has not a stationary solution, but we decided to start it from a random distribution. The red constant will control the mass in the system. And if we represent the pressure against the unit of the volume, 1 over rho, we recognize here a van der Waals curve. So we have the both states, liquid and vapor, and the random distribution will act as seeds toward a phase separation and will obtain either a liquid drop in a vapor atmosphere or a bubble, a gas bubble, a vapor bubble in liquid. So for lower mass, we'll see here how appears a liquid drop. Here red color means density high in the gas phase. Now we make the density higher, and for the system it's hard to decide between drop and bubble. So this structure, like a two-layer system, persists for longer time, and now the density becomes higher, and we'll have a bubble in a liquid box. So the position of the droplet depends very strong on the boundary conditions, and from here comes the idea to study the contact angles using the phase field model. When we speak about contact angles, we have all the time this sketch in the head, a small liquid drop sitting on a solid substrate, and along the contact line, we have to have the equilibrium condition, the Laplace relation. Theta is the static contact angles. And the idea started from a paper from Len Pisman and Yves Pommeau, published in 2000, Physical Review E. And in place of controlling directly theta, we'll control the contact angle through the density at solid boundary, rho s, a parameter varying between 0 and 1. In this paper, they have derived the interfacial energies, solid vapor, liquid solid, and liquid vapor, in the phase field terms. They have replaced into the Laplace relation and found an analytical formula which relates the static contact angle, theta, with the density at the solid boundary. So for rho s between 0 and 0.5, we'll have hydrophobic surfaces, and between rho s 0.5 and 1, hydrophilic surfaces. So we put this in our numerical simulations. We are under the periodic boundary conditions. Top rho s is rho is 0, and down will be rho equal rho s. And we found a very good agreement between the analytical formula and our measurement from numerical simulations. So we can see at the substrate that all the time appears a precursor film. Here cannot be seen very good, but it exists also here. But when the surfaces become hydrophilic, like here, this precursor film can be very good seen. So here I'll present you the dynamic contact angles, a movie for a sliding film on a sloped plane, but here it's not sloped. So the film breaks up into more droplets, which will start to run and will start to catch each other. Maybe I'll go a little bit faster. Oh, maybe it was too fast. Here we'll catch the last one. Oops. And we are under the periodic boundary conditions, and we'll have a constant velocity. We observe that we have two different contact angles. One in the, we'll have here the advancing, and in the back the receding contact angle. And we have also represented how it looks, the flows inside the droplets for different rho s, for different contact angles, and seeing that the liquid rolls. So the droplet rolls on the inclined plane. Now the next step, the substrate, it's not anymore homogeneous, now will be heterogeneous. So we have hydrophilic stripes which alternate with hydrophobic stripes. And the thin liquid layers will break up, don't want to sit on the hydrophilic surface, don't want to sit on the don't want to sit on the hydrophobic stripe, want to sit on the hydrophilic stripe. And now, making the thin layers thicker, we can see the flow inside the layers. So here at the substrate, we have uncompensated forces, and this will lead to flows from hydrophilic to hydrophobic stripes. And this will maintain the layer wavy for longer time with peaks on hydrophobic stripes. Now I will show you some simulation from 3D. So we have again a thin liquid layer, and the substrate is patterned, chemically patterned, for example, and we can obtain regular structures, so design liquid structures and contour pattern formation, and even more, if this pattern contains an information and will lay out a liquid layer over the substrate, we can decode the information. So this is so-called functional surface with application for microfluidics. And the last application, which I'll present today, is connected with my work in the last 4 years. So this was motivated by a common project with Stefan Karpiczka and Hans Riegler from Max Planck Institute in Potsdam, Germany. So we started in 2008 or beginning of 2009 with this work. So they made here, these pictures come from experiment that are from the experiment of Stefan Karpiczka. He's also here. So what we have now, we have 2 liquid drops in a gas atmosphere. The contact angle is low, between 10 and 20 degrees or maybe more. And they showed here, so the 2 drops have the same density, the same viscosity, the same contact angles, but different surface tensions. And when will be put together in contact with each other, it is expected to appear a coalescing assisted by Marangoni forces, so acting from lower to higher surface tension. And here on these 2 rows, there are shown 2 kinds of behavior illustrated by Stefan. So here we have on the first row, so-called a fast coalescence. So it's a quite normal coalescing with a little bit pushing effects to the right in the direction of the Marangoni forces. Here it's lower surface tension. And looking laterally, we see the bridging film increases continuously till the minimum between the two drops disappear. For the second case, when the surface tension difference becomes higher, one can see that the bridging film remains shallow for longer time, so the 2 drops run one after other without to coalesce. So this was the aim of the project, to find different solutions. One of the solutions was to make the simulation using the phase field model. And in this case, we need a new variable in order to distinguish the liquids. So the liquids are perfectly miscible. We don't need so to say, a surface tension between the 2 components, but we have to distinguish the two liquids. And in this case, we have again Marangoni forces, but not induced by temperature gradient. They are induced by the concentration. And again, the surface tension decreases with the increase of the concentration, so K decrease with C. And we have now in our system of equation, again, the Navier-Stokes equation, the continuity equation, and an equation which describes the evolution of the concentration field. So the conservation law for the partial masses. So I would like to say here that we have chosen in our simulation, in fact, everywhere C0, also in the gas phase, in the vapor phase, only it was C equal 1 for one drop, for drop 1 in this case, and only so the diffusion was, so this equation in this way acts only in the liquid phase, so only between drop 1 and drop 2, will not have a diffuse in the vapor phase. So we managed to find the experimental findings, and here I would like to show you some results from 2D showing the concentration and the flow fields inside the layers during the coalescing at different times. We can see very well here the Marangoni flow from lower to higher surface tension. Here the velocity are high, exactly like in the experiment, and appears here a vortex, observed also in experiment. And about this topic we'll speak maybe later, Stefan more. What I want to illustrate here, I want to show you some pictures and movies coming from 3D simulations. So in the case of identical droplets, everything will be very symmetrical. And here the coalescing is already done. And after that, the system will relax to the spherical shape. And I'll show you also a movie, seeing from the top and from the side. So now we'll have an elliptical drop which will relax to the spherical shape, to the circular shape. And when we have coalescing assisted by Marangoni effects, we'll see that the coalescing is asymmetrical, and it is also pushed to the right, and here we'll find the rest, will remain at rest. So we observe a propulsion induced by surface tension gradients, observed also in the experiments of Mathieu Cellier from Canterbury University in New Zealand. And I'll show you also the movie. So we observe the pushing effect to the right. Maybe we'll go a little bit faster. Which one you mean? So, okay, why to be completely? I have a contact line. Why to be when I look at the drop from the side? Yes?
However, it's not the same scale on the vertical.
Yep.
It's not the same scale on vertical.
Squish. Yeah. Okay. And
I'm very, very close to the substrate. So, in conclusion, the phase field models are free of interface conditions and easy to be implemented numerically. They show a good agreement with the classical models in the limit of sharp interfaces, and we have presented as applications the Marangoni convection in two-layer systems, drops and bubbles, static and dynamic contact angles, behavior of liquid layers on pattern surfaces, and the coalescing of drops with different but perfectly miscible liquids. And for the future works, we are interested about behavior of thin liquid layers and droplets on shaking substrates. So for the liquid layers, we'll speak about the Faraday instability. And here I have a preliminary result. This is a droplet sitting on a solid substrate, and we shake in the X and in the Z direction. And we'll see that we'll get a driven motion to the right because the droplet moves more to the right and less to the left. And with the time, we'll have a driven motion to the right, so to say, a ratchet system. But how I said, this work is still in progress. Yeah. Thank you for your attention.
Questions?
Did you have also non-coalescence?
Yes. But I didn't show here in this presentation, but I have the movies at me. I can show you. Yes, of course.
And
But
do you have a comparison with Stefan's?
so we compared. We found a good agreement. So a qualitative agreement. So in the same range of the velocity, what we compare in our paper from European Physics Journal. We compare the velocities in the bridging films. We compare from the experiment. It was a lubrication model and a phase field model. So this was a direct comparison with experiments.
In the case of the heater treatment substrate, I did not understand why there was a flow. Was this just a transient, right?
But it is because of the wettability contrast between the two stripes. So we have not the balance the forces along the substrate. So
It should only be
with the time,
it should only be a transient. I mean, it should stop. Then.
will stop. Yes, will stop. If so, because of this transport, so will come an adsorption, desorption phenomena, and will have in one moment the same rho as the solid substrate. But how long we have the possibility to keep all the time the same rho s. So we have the continuous motion inside there.
Yeah, but then I didn't understand how do you model the heterogeneity because it should be a different rho s.
But there are different rho s. So I put it as, so this was like a play. So I played with the boundary conditions at the substrate. So they were different rho s. We go from back here. Maybe I was too fast and I didn't explain. No. Doesn't. Okay, now. So we have here 2 stripes, here 4, here 8, here even more. So with the time, this wettability contrast will disappear, and also the film will become flat again.
In the propulsion experiment that you showed, I'm a little bit puzzled by the consistency with the balance of linear momentum. So these are internal forces, and they produce overall motion of the drop. What is wrong with my interpretation?
We have 2 liquid drops which are sitting on a solid substrate. The 2 drops have different surface tensions, and they'll be put in contact with each other, and the motor which push the forces are the surface tension gradients between the 2 droplets, but they are sitting on the substrate. So it will be the same problem, but so in a flying system, so everything open and 2 droplets. This is very interesting idea to take, for example, two drops with, like in a microgravity, so without gravity forces, not to be connected with the surface.
Yeah, but let us stay on the
They stay on the
be in
surface.
unbalance. I mean, some forces must be unbalanced in order to provoke this overall motion.
We have forces between substrate and liquid. Can explain this to the forces between the substrate and the liquid.
And have you checked this unbalance of force? Normally you can in your simulation.
So I didn't check how it's so exactly one-to-one, but so I checked the conservation of the mass, the conservation of the energy, the conservation of partial mass, but not exactly this balance.
But also linear momentum
Yeah,
should be.
Yeah, but yeah, okay, I said if I started from the Navier-Stokes equation, which is also the momentum equation, I have also the conservation of the mass and of the energy and the partial masses in the system. Okay, but yeah. Yeah.
But concerning conservation of energy, already in one of your first models had one with the Marangoni effect and
Just by the
and,
temperature grad.
coupling with the heat equation.
Yeah.
I was wondering why you didn't have the source term in the heat equation, namely something which is given by the viscous dissipation in the Navier-Stokes equation. So this should create temperature, and therefore I'm not sure whether you can get an energy balance there. So my impression was that there are terms missing. Probably you, as a physicist, you say
Yeah,
that
yeah,
they are
yeah,
of small
yeah.
order, and I can
I
throw
think
them
the
away,
most
but,
important terms which, yeah.
but
So that this form which is very used also in the numerical simulations, but it's not the complete form of the
yes, and
yeah.
also
There are-
related to this, so if these terms are missing, so what can you say about stability? So for instance, which density ratios cause problems, which density ratios are still okay?
Yeah.
No, I mean, so if the mass density ratio between vapor and liquid, for instance, is a factor of 1,000 or something like this. So
It's a difference of 10 of minus 3, 10 of minus 4.
yeah. So does this still work? Or yeah. Okay.
Actually, for rho, you have only convection equation.
Yeah.
You don't have any kind of diffusion. Or
No. Yeah.
And this is numerically stable.
Yeah.
That's okay.
Yeah.
I mean, also the rho should not be confined to interval 0, 1, and you should get with your concentration equation. I would check.
Okay.
Anyway, we have to go to the next talk.
Yeah,
We can discuss later.
we'll discuss.
We have plenty of time then. Yeah.
A short
Last
question.
question.
Yeah, kind of try to find some maybe similarity. Maybe you can help me. So there's experiment that was I don't remember who did it, but the idea was you have a substrate it covered with some surfactant, and there is a droplet. I think it's sitting in the liquid, and then this droplet dissolves surfactant, and because the system is unstable, so it's dissolved on one side, and then it starts running in the dish. Right, and the running in the dish because you have different contact angle on front and on the back. So isn't it kind of similar in a sense to your story when you have essentially two droplets when they merge, you have different contact angle on front and back, and then they start running. Kind of maybe explain the
Yeah.
when the momentum takes.
Yeah. Mm-hmm.
Best Romina.
Right.
Mm-hmm.
It was PRL or something, right?